Hi everyone, my name is Shoumik. I'm from the Material Science and Chemical Engineering Department, and today I'll be talking about nanocomposite hydrogel as soil additives. This study is part of a bigger project that involves soil modification, where the idea is that we're replacing the pore water, which is the water found in the spaces in soil, with other chemical or biological based solutions. And one sustainable candidate is the biopolymer-based nanocomposite hydrogel, which you can see has enhanced properties and can retain higher amounts of water. So to run our simulations, we first create a model. Our model includes polymer chains, which are in the shape of these beads connected by springs as bonds. And we also have nanofillers in the shape of hexagonal platelets. Our model is different from previous hydrogel study in the sense that we have included explicitly solvent particles as well, because water is a big part of any pore water system. All of our bonded interaction is defined using the Feeney potential, and all other non-bonded interactions are defined using the Leonard-Jones potential. So before we run our simulation, we have two different types of polymers in our system. They can either be repulsive or they can be attractive. And we also have a system which we name as control group because it basically contains only one type of polymers. So if we look at the stress autocorrelation function, we can get a qualitative measurement of viscosity depending on the end values of the graph. So if we can see with an increase in nanofillers, we see that there is an increase in viscosity, which means our hydrogel are getting stronger. One thing to notice is the moment we see a non-zero tail on the stress autocorrelation function, that is where our hydrogels transition from a solution to a more solid-like state. To explain the viscosity trends, we can look at where we performed a network clustering algorithm. This is basically where we try to see the connectivity of polymer chains to the nanofillers. What we can see at low filler fractions and in repulsive polymer cases, we form these little individual clusters in our system, which in turn means that it does not have it is not mechanically stable because these clusters are constantly breaking and regenerating. But as we add more fillers or we increase the polymer-polymer interaction, we see that these clusters are coalescing into a bigger system, which is more mechanically stable and hence has higher viscosity. Finally, we can support all our results with a simple non-equilibrium study called the step strain test, where we stretch our system and we measure the stress relaxation. We can also see with the increase in fillers or the polymer-polymer interaction, we see that the normal tension is higher, which means that our hydrogel have a higher elastic energy and hence are stronger. Thank you for your attention, and I'll be free to take any questions.
In the left lower equation, what's the bar mean? Is the radius of
It's the distance between the particles. And RC is the cutoff distance beyond which we don't calculate any potentials or the interactions between the particles.
What is the purpose of adding these two? So you increase the viscosity. What is this used for?
So this makes the soil stronger. All this time, soil strengthening was done through, say, cement, which is not sustainable.
Okay. So
But using these biopolymers, they are made from a bacteria, and once it has done its job, it is easily degraded.
Okay.